Good morning. Things happen, so um, actually, original plan was to have a back-to-back talk with Jan sitting over there tomorrow morning, but well, let me do my piece today, and Jan will follow up on his things with more detail. So, my job is supposed to be a review of word crossing, but word crossing has become such a huge subject that has many applications not only in physics but mathematics as well. So I will have to confine things a little bit, and the key word here is the constructive. That means we want to see actual BPS particle the way they look like in real space. So these are some of the relevant references I'm going to mention. And in particular, my own contribution to this subject was possible thanks to the collaboration with these many young, excellent people. Jaolong Wang, a postdoc, Seungju is also a postdoc, my student, and Songjae you already know. So word crossing is something that happens to BPS state that's supposed to be stable, but we learned over the years that these BPS state preserve 4 or less supersymmetry. Things happen. So when you change the theory slightly, either parameter of the theory or vacuum expectation value of the theory, sometimes state just disappears across certain worlds. So this is called marginal stability worlds. So we would like to understand why such a thing happens and what kind of things exist on the two sides with what degeneracy, what supermultiplet. That's basically word crossing problem. So before we get to more recent story, I'd like to sort of remind a little bit older history, 20 years ago, 10 years ago. So the first, I think at least in the 4 dimension, there was the earlier example in 2 dimension by Chakotay and Baffa, but at least in 4 dimension, it was in the Seiberg-Witten theory that this discontinuous spectrum was observed. And in particular, in the rank 1 example, I think the first construction of the weak coupling spectrum was actually by Gontlet and Habe in 95, and they found this sort of single dionic tower. And then later, Villar and Ferrari spent a lot of time trying to understand what kind of strong coupling spectrum there should be that's consistent with the monodromy. So this is typical example you find, for example, if you don't have a flavor, a little bit more complicated spectrum if you have more flavors. The question of higher rank example is much more difficult, it turns out. Not much was found for a long time. Lohe, for example, in year 2000, using boundary conformal field theory construction, discovered that there are roughly speaking rank squared number of dions in hypermultiplet in the central point, the so-called Gepner point. Outside, you have essentially infinite number of marginal stability worlds and infinite variety of dion. So that's very difficult question to address in one shot. Why such a discontinuous spectrum happens, or even though this is supposed to be stable under the supersymmetry argument, was actually first understood in slightly different context than you think. It was actually first understood in terms of quarter BPS dion in N equal 4 Yang-Mills theory. That was started by Ashok and Dasgupta Mukhi's observation. There is something called string junction. Bergman took it and realized it by having open network of string junctions as a quarter BPS object where he could see marginal stability rather explicitly. And these people are a little bit curious how that would look like in real space in terms of classical soliton. And this leads to the picture back then to the following statement that if you try to look for classical solution in the weak coupling regime, typical BPS state looks like not single soliton, but many solitons that are bound together by some sort of classical force. So that means immediately word crossing happens simply because one or two more of this distance become infinite, so that at some point as you cross this wall, such a state no longer exists as a one particle state. So that's all there is. It's completely classical physics, if you will. that also means, though, if you want to ask a little bit more detail about this state, such as degeneracy, what you need to ask is just write down relevant supersymmetric Schrödinger problem and ask how many states there are, what kind of angular momentum they carry, etc., etc. So this was done beginning from this monopole-based weak coupling approach. And typical state we found back then was to have this bunch of dions, for example, SUN theory that's broken to Coulomb phase. And this is we call a dion chain. And degeneracy of such a thing was counted. And the supermultiplier was found to be, oh, this was in n equal 2 context, not n equal 4 context actually, is the basic half hypermultiplet times bunch of angular momentum multiplet. And if in terms of more modern way of writing the degeneracy of this in terms of the so-called secondary trace, you find a formula that's determined entirely in terms of this Schrödinger product between interacting pairs. And in particular, these are solutions, the quantum states that appears in rank 2 and higher example. And as you saw here, the spin content of this is unbounded, basically is given by this Schrödinger product. And the electric charges in this dion chain can be arbitrarily large. So it immediately implies that there is an arbitrarily high spin state in your asymptotic spectrum. And each and every one of these dions decays somewhere. So you have infinite number of marginal stability world that extend all the way to the asymptotic region. In fact, curiously, last year, this sort of phenomena was rediscovered in, of course, much more sophisticated technique now. This was constrained to weak coupling study. Around that time, the Philip Agiles and also group at Minnesota tried to sort of emulate what happened in this quarter BPS picture of this string web picture in terms of Seiberg-Witten theory by trying to look for essentially UV incomplete soliton solution, multiparticle soliton solution. And if you take that seriously, picture you would get in, for example, vanilla SU2 theory is that your vector meson that should disappear at some point is really two particle bound state of monopole and dion like that. And that should be exactly what happens here. Okay. What makes the study of wall crossing much more interesting and much more generic was, as many of you already know, is Frederick's contribution. He realized that this multi-center thing is very easy to see if you have abelian system. And therefore, in the supergravity, typical supergravity picture is all abelian black hole solution. And there he found this very generic distance formula where distance between any pair of particle A and B is this R, and this is again Schrödinger product. This is a central charge of this with zeta being phase of the total central charge. So this multiparticle picture persists, of course, in the black hole regime as well. That's what was found back then. And then a couple of years later, Frederick wrote down quiver dynamics, how to approach and count this kind of state. And there is also a very important paper by Dunef and Moore a few years later. Okay, so that's very brief prehistory of the area. So as we all know, about 5 years ago, something big happened. This pair of mathematicians, Kontsevich and Soiberman, came up with this incredible formula that supposedly tell us what the degeneracy is, what the discontinuity is. So before we actually get to this more recent development, let us very briefly again look at what happens there, because it will also set up some of the questions we are trying to answer in this real space wall crossing business. So what is Kontsevich-Soiberman formula? So you given a charge lattice with lattice point alphas and betas, you define a Lie algebra object V like this with again Schwinger product alpha beta, and you define the exponentiation of that, this is sort of like group element, which looks a little bit strange because you have again infinite sum inside this exponent, and you simply demand that across the wall the string of this operator on one side that's weighted by this exponent omega, which is essentially degeneracy of the particular state, be equal to each other. Of course, you need to specify what's the ordering here and what's the ordering here. The ordering is dictated by the phase of the central charges of individual gammas. And as you cross the wall, typically the ordering changes because at the wall, the phases of central charge aligns. And this omega is so-called second Helicity trace. That's the relevant, the index for n equal to BPS state. Now, one thing that's really, imagine this is lattice point. So just multiply by an integer. So that there is also lattice point like this. So there is a relevant real algebra element again. So as you just saw, it's kind of strange combination to see in the exponent. There is different way of writing exactly the same thing, it turns out. Instead of doing that, but just do exponentiation of individual v like this, except you replace this exponent, not this individual degeneracy, but what we call rational invariant, omega bar. It's p that divides gamma, I sum over. This is some finite sum. Okay. So this curious rational invariant appears, and you can ask about this rational invariant, or you can ask about this invariant. It's exactly the same thing. It's equivalent. Knowing one implies the other. So, I mean, it was given to us, and we want to understand it. And of course, the first question is it really true? I mean, when they did this, they checked all the existing formula back then, I think, in particular, a lot of rank 1 example. And there was primitive and semi-primitive word crossing formula that DNF and Moore wrote down. It conformed with that. But there are more to word crossing example to that. So, is it true physically? For my own things, I would like to see this sort of thing directly from construction of the state. So that's what I'm going to talk about later. And in particular, this curious appearance of rational invariant is something we'd like to understand. Also, in here, the spectrum on the smaller side of the wall is typically input in order to get the more complicated side. So there is certain input parameter you need to understand in order to really address physical spectrum on the both sides. So that question needs to be answered too. So generally speaking, I mean, in the simplistic example you have seen, it's typically omega plus equal omega minus equal 1, which means you start with certain hypermultiplets. But generally, as we will see later, that's not true. We have large number of state on the left-hand side, right-hand side of same charge, typically different degeneracy, but there are part of it which is invariant. So these are questions we'd like to address. I mean, again, this is supposed to be a review, so I cannot help saying of just few words what happened, what people did, and in particular, of course, these three gentlemen, Gayotomo and Naitsuke, did during the last 5 years. They essentially proved the Konsevichi-Soberman formula, at least for Seiberg-Witten theory. By putting the Seiberg-Witten theory on a circle, they observed some Stokes discontinuity phenomena. They tried to realize this in a very several different way. Along the way, encountering 2,0 theory, Hitchin system, Dabu or Fock control coordinate, framed BPS, spectrum generator, and all that. So a lot of things happen. So I mean, I guess this is essentially a proof, fairly convincing proof for general Seiberg-Witten theory. The Konsevichi-Soberman formula is the correct formula. So there is certain holomorphic quantities called Dabu coordinate you can define for each and every one of these charge lattice point, which is function of the vacuum moduli and some fictitious parameter theta, unphysical parameter theta. There's a discontinuity along this theta, which is encoded in terms of this Kontsevich-Zollman, the operator of Kontsevich-Zollman. And the continuity of physics across the world is implied by this discontinuous spectra, which I find extremely remarkable. So out of these kind of, in the effort to prove this from various approaches, one of the things I find very interesting is notion of spectrum generator. It turns out in some cases you can compute this holomorphic coordinate for two different data directly. So if once you of course compute these two directly, these two are supposed to be related by action of this the Kontsevich-Zollman string operator, which knows about this degeneracy. So in principle, once you compute this and once you compute that, all this information is there. So this is what they call spectrum generator. Of course, unraveling this, what this precise operator is in practice very difficult thing to do in most cases. And then there are other construction. They realize this BPS state, in particular hypermultiplet, as a geodesic segment on Guyot curve that allow them to reconstruct the entire SU2 theory spectra, except I think the four flavor case. There is much more general things you can do by giving some certain set of rules how to read up what they call BPS quiver from triangulation. And using this technique, there were recently development for rank 2 and higher examples through this work. By the way, I have to apologize that my reference list is rather incomplete. I was hoping to have one more day to fill that up, but that's my excuse. So if any of you have a complaint, please tell me and I'll add it on. So much for the background for the main thing, content of this. So, I mean, this Kayoto-Monaitsuke work was very convincing for Cyber-Witten theory, but we really want to understand for all physical BPS spectrum. And in particular, I would like to do that by building up, by giving a method to build up recursively, basically, all these possible spectrum in any given physical theory. And in particular, along the way, we will be able to answer why this funny rational invariant has to make appearance in this story. And a little bit later, we will talk about how to deal with this input data as well. So this is what I call real space word crossing. So as I said before, the word crossing happens because of this multi-center nature of typical BPS state. And in order to count the state, you just need to solve Schrödinger problem. So in order to do that, it turns out what's sufficient is essentially sum over all possible two-particle interaction. That does not give you complete low energy dynamics, but it does give complete low energy dynamics that's relevant for the index theorem. So for example, treat n-1 of them as if they are just given background. Treat one of them dynamical. And for this, because we are very near the world, the distances between these charge centers are arbitrarily large. It means that whatever happens at the core is completely irrelevant. So you don't need to worry about this non-abelian part. So all you have to do is write down BPS equation that comes from the Cyber-Witten theory, which was in fact attempted by these gentlemen long time ago. And in particular, one of the things that was very simple at the end of the day is if I look at this central charge function. So this is not central charge, but it's actually function of the position, because this field I put in is field that's a solution to this various background configuration. Has extremely simple form, where it is determined essentially by the Schwinger product between this interacting pair and this single number that you have seen in Denev's formula. uh, we realized that some time ago that if I have this very simple situation where we treat one of them as dynamical, the low energy dynamics, for example, bosonic part, can be written entirely out of the central charge function. And well, this is essentially the Dirac force, the Lorentz force, and this is like Coulomb force, and this is like force that's mediated by scalar. And because we are very near the wall, we can approximate this part in terms of imaginary part squared. It turns out this final form is exactly what you should expect from supersymmetry. The remaining four supersymmetry this BPS state should have. So we do that for each pair and then just sum it up. Treat all possibles, all the particles as dynamical on equal footing. That give us the interacting part of this multiparticle dynamics precisely. It does not give you the kinetic term part precisely, but that's again irrelevant because we are going to do things far away from each other. In particular, this interacting part is not really new. This is exactly what Dunef discovered 10 years ago in the context of multi-center black hole solution. But supersymmetry is same, and that's of course why exactly the same structure has to arrive. You might wonder, I'm using Seiberg-Witten theory in the arbitrary place. It's a strongly coupled place, so how can I write an approximation like this? It turns out what happens is this proximity to the wall acts like another small parameter. So it's not small electric coupling that let me control, but it's a proximity to the wall that let me control these interactions. So if you look at any given pair of potential, there is a bosonic potential that's repulsive near core and attractive far away if this parameter and this Schwinger product has same sign. If they are opposite sign, it's runaway potential. So if you have an attractive potential with some minima like this, you have bound state, and of course you have BPS state. If it doesn't happen, they run away to infinity, and that's exactly why wall happens. So relevant wall crossing parameter here is this sign of this guy. But you see, you have this minima. So I set up a low energy dynamic such that individual particle has 3 collective coordinates, which is just position. But the position is constrained like this to the distance between any given pair be fixed. So that should imply there is some reduced problem where I need to deal with not 3 n-dimensional moduli space, but 2 n-dimensional compact moduli space. In case of 2 particles, instead of R3, I would be dealing with S2, for example, which is typically easier thing to do. There was a little bit of minor confusion about this over the last 10 years. It turns out even though there is this potential that apparently lets you settle down to this classical moduli space, that actually is not dynamically allowed thing to do. And the reason that happens is that there's mass gap you see here is always equal to the mass gap, quantum mass gap you have simply because the classical moduli space has finite volume. So remember, this is a quantum mechanics rather than quantum field theory. So finite volume itself, even though you don't have any potential, generates a mass gap. So you cannot truncate to this. But on the other hand, we have all learned how to deal with such things by doing deformation and localization. You just change the theory in such a way that index doesn't change. So that's what you can do. And at the end of the process, what we find is basically 2 n-dimensional nonlinear sigma model that's coupled to abelian line bundle. So it's essentially at the end of the Atiyah-Singer index theorem you are supposed to solve. So this is the usual n equal 1 nonlinear sigma model. And it's the index of this that you want to count. So after read a long history of this field, this multi-center business, we finally know what is the right, exact and right index theorem to use is nothing but the usual Atiyah-Singer index theorem. Where the most important thing is, of course, this line bundle, the curvature of the line bundle, whose strength is given by all these pairwise Schrödinger product. Well, that's only step 2. I have 3 more steps to go in order to have the final answer in this approach. The step 2 is next step is to realize that in order to understand generic state, you typically have to consider state that's built up from many identical particles. So already in this SU2 example, in order to build up this ion chain outside, you have to use many of these identical particles. So that means you have to insert overfolding operator to take that into account, like this, which gives you essentially an iterative sum. So the sum over free part of the manifold under this permutation, some self-fixed manifold on the part of the permutation, and so on and so on. And you end up with the iterative sum of various multi-particle problems. All the sub-problem has small number of particles involved, but you have to sum over all of them. So if you have large number of particles, n number of particles in question, you typically have to sum over n factorial number of such problems. There is a very interesting key element here is when you get contribution from the fixed manifold, it's not just this fixed submanifold, but very small tubular neighborhood around it that also contribute to the index. And turns out there is a universal number you need to associate with that. So instead of telling you how you get the number, let me just tell you the end result. This universal multiplicative factor that comes with this submanifold contribution can be computed. So if the original particle was gamma and you are thinking of p identical gammas in the same problem, that contribution turns out to be omega gamma divided by p squared. So remember there was this rational invariant that made appearance in Kontsevich-Zollberman, where I have sum over all degeneracy divided by gamma divided by p, and the whole thing divided by p squared. And this is the origin of this. So this was discovered by us in this direct approach by setting up index theorem, but it was actually discovered 1 year earlier before us by Mansfield, Piljin, and Sen. Related but slightly different argument. It's again, of course, related to statistics, quantum statistics. So at the end of the day, you assemble all of this and you find this rational invariant making an appearance, and the discontinuity of any given charged object along the omega minus, that is the one side of the wall and the other side of the wall, the difference of the second Elliott trace. The basic index theorem is again Atiyah-Singer, but you need to multiply this rational invariant divided by statistics factor. Gamma is like basically p factorial. You have this sign that again needs to be understood from this first principle computation, which we did. And you have essentially sum of all possible partition of the charge in your starting point. So you might think this is not very practical. But as the Jan will talk about tomorrow, this group, the MPS, successfully found a routine to compute this index in an equivariant setup. Okay. And that will, in such a way that at the end of the day we can put everything in Mathematica and compute any given situation. Again, of course, this is not end of the story. We need to evaluate this index, which we didn't do, they did. In fact, it was much easier to the equivariant version of that because you have fixed point theorem at the end of the day that way. And you should come to Jan's talk. Oh, there's something. I mean, on this when you define this equivariant index, there is only one the isometry you can really use for that, which is angular momentum. So this might sound a little bit strange because supercharge is supposed to be typically doublet on the angular momentum. So how can you write the object like that? It turns out this is remnant of this reduction to vacuum moduli space, the classical moduli space. And you can sort of trace it back by going back to our initial picture of 3 n-dimensional moduli space and make contact with this by now rather well-known protective spin character. So this, what I thought was angular momentum in the final story, is not really angular momentum, but it's actually sum of angular momentum and the SU to R, in case of field theory, of course. And finally, there was routine that compute this all of this explicitly as some sort of invariant polynomial. And Ashok took that a year and a half ago and decided to compare against what happened, what formula you would get out of Kontsevich-Soiberman routine. And with two mild assumptions. One is that all the relevant charge is on a single charge lattice plane. But that's sort of what you expect anyway near any given marginal stability world. All the relevant particle in this multi-particle picture better be on a single plane. Otherwise, if you do not have that, it's like having you are very near the more than one marginal stability world. So that's rather mild assumption. And second is that in the absence of so-called scaling regime, and in terms of what I'm going to say a little bit later, in the absence of quiver invariant, under these two assumptions, Ashok was able to show complete equivalence between formula you get out of this equivariant computation and relevant Kontsevich-Soiberman. So this is another sort of physical proof that Kontsevich-Soiberman works with some additional assumption. So this addresses in particular a lot of field theory example. It covers some of the black hole example. So it's not same set as the Guyot-Moore-Knight's proof. Okay. So I promised that I will answer several questions. So the first part, I think I'm done. The second part, where Kontsevich-Soiberman, you need some sort of input parameter in terms of certain the degeneracy of basic constituent particle. We don't have complete answer to that, but we have some sort of partial answer to that. So that's what I'm going to talk about. Of course, for that, we want to go back to Frederick's quiver picture before. So quiver, for example, one way of thinking of this is by realizing any given BPS particle as 3 cycles wrapped by D3 brane and relevant low energy open string quantum mechanics on it. So you have a bunch of UNs where K is essentially number of particles of any given charge, and there are a bunch of bifundamentals, and the number of bifundamentals is same as the intersection number between these 2 cycles. There is so-called Coulomb phase, although it's mechanics, so notion of phase doesn't really exist. It's some sort of truncation. In the Coulomb phase, this multi-center picture of BPS state emerges again. In fact, the end result of doing this, when you integrate out this bifundamental, is exactly what we did earlier. So whatever we were doing earlier, you can import, verbatim to this setup. Which means what we are doing is not just field theory thing, but also applicable to black hole situation. Excuse me. There is the other approximation, which is relevant when the phi Helioplus constant on this node become very, very large. It's so-called Higgs phase. And in there, you typically get some sort of quiver variety, and if you have additional superpotential, some sub-variety in that quiver variety. And again, in this picture, you have, again, word crossing problem in the sense that if you go one region of Fi constant, you have one spectrum or one cohomology. If you go to another region, you have another cohomology, and the two cohomology doesn't agree. So that's Higgs phase version of the wall crossing problem. And again, this parameter that the central charge divided by phase of the total charge, so total central charge and imaginary part thereof, is the one that takes role of this that measures the distance to the wall. And of course, relevant thing is to count the cohomology. So when Dönef found this way of describing generic BPS black hole, he was hoping that perhaps you can do either one and end up with the same number. And in fact, in the older example he considered, this was true. He checked, essentially case by case. And in this Ashok's proof a year and a half ago, he also demonstrated it in a rather general fashion under these two assumptions I mentioned about. So I have these two computations that looks very similar to each other, and in fact, in many situations, you can show why they have to agree. And that this happens basically, again, it's quantum mechanics rather than quantum field theory, and there is no two different phase to this problem. However, this equality is known to fail, and I think the first place I saw was again Dönef and Moore in 2007. It fails apparently when there is a loop of quiver, that is possibility of superpotential. So what happens? So let's take very simple example. This 1, 1, 1 is an abelian quiver. Intersection number 4, 5, 6. This has 3 regions, and each of the 3 regions you have completely different vacuum manifold. In one region, you have this Hodge diamond for your manifold. You have this Hodge diamond. You have this Hodge diamond. So you see the vertical part of these Hodge diamonds are all different. So these are the one, and you should think of this vertical quantum number as actually angular momentum. They are literally angular momentum. So you have angular momentum doublet, you have angular momentum 2 angular momentum doublet, and etc. And you have this. But note that there is a part that doesn't really change as you go over to the another side. So what's going on? They found basically you can split into 2 parts, and one part looks exactly like what you found in the Coulomb phase computation. This was simple enough that they could do Coulomb computation. There is a part which is insensitive to where you are, and in particular, if this intersection number happens to be very large, this number is actually exponentially large. So that's why you see a little bit larger number here than numbers here. So apparently, if you go to the Higgs phase, you see something more than Coulomb phase in general. So it seems what's happening is that across any given wall, there is a part of Higgs index which is intact as you cross the wall, and there is a part that is not intact across the wall. So there is a wall crossing part and wall crossing safe part. Remember that in Kontsevich-Soibelman, we needed some understanding of degeneracy of state if the state persisted on the left and right side of the wall. So this essentially generalized this hypermultiplet you started with. It's much more complicated, but it's essentially same physics. So question is, how do you isolate this guy? And for the wall crossing, how do you sort of use the knowledge of these guys in this full wall crossing formula? Because as I said before, Coulomb computation I showed you so far somehow fails. So somehow I need to feed this back into the wall crossing formula. So that leads us to the notion of quiver invariant finally. So in all examples where omega Higgs and omega Coulomb coincide, in almost all examples, what you can see is there is no loop, or there is no superpotential whatsoever. Okay, so, and the vacuum manifold is simply symplectic reduction of whatever bifundamental fields. in examples where this happened, typically you have this superpotential. Of course, once you have a superpotential, you have F term in addition. So the real vacuum manifold is this guy, not this guy. Okay, and I mean, in some abelian, simple abelian example, in particular, you can make it to be the complete intersection. Therefore, you can compute things. And it was realized last year by two independent groups that this you can essentially split the cohomology of this, which should count all the physical BPS state, into two parts. One coming from pullback of cohomology here, and whatever's left behind. The relevant index in the equivariant index is this Hertzsprung polynomial. And you compute this, and what one realized is that by just computing this thing and omega Coulomb completely separately, what one observed is that whatever you found in the equivariant computation for the Coulomb side of phase is exactly matched by this pullback part. And since all of this wall crossing phenomena happen simply because of this multiparticle picture, what has to happen in this Higgs version of this approach, that this part is not invariant as you cross the wall, but this part is actually invariant. So you can show all of my statement step by step separately. So I mean, any of the statement does not rely on the other. Okay. So this is what we call omega invariant or omega intrinsic. This should have been earlier, sorry. In particular, this is in case of abelian quiver with a single loop. It's sufficiently simple geometric situation. You can compute everything explicitly using existing things you find in the algebraic geometry technique. This D-term variety is essentially bunch of CPs, and you have a complete intersection inside it as a true vacuum manifold. You compute the relevant index there, and in terms of some counter integral, and you split into two parts. One part that seems to depend on where you are in your phi Elliott plus constant plane, and the part that seems to be completely irrelevant to that. And looking at this and repeating what Dunef and Moore did for the 3-node case, you can see that this part is generically exponential in terms of this linking number. These are always at most polynomial. And this agrees exactly with Coulomb computation that you would find from this equivariant index computation. So let me give you some example. This is again for the simplistic 3-node case with the linking number 888. This vertical part is again 1, 2, 3, 4, 3, 2, 1. These are wall crossing state. This is the case where this structure, Hodge diamond, doesn't really change, but that doesn't mean that they don't do wall crossing, because all of this state disappears if you land on the wall. However, this horizontal things with these large numbers doesn't change at all. It's completely invariant. You can give physical interpretation to the vertical line as a helicity. And in the field, if this system came from field theory ion, you can give it R charge interpretation on the horizontal. So this is typically what happened. So there is a vertical part and there is a horizontal part. Horizontal part is invariant under the wall crossing, is typically exponentially large in numbers. Vertical part always agree with what you saw in the earlier real space index computation. So there is apparently this split of this true moduli space quantum state counting, where part of it changes to wall crossing and is characterized by angular momentum multiplet, and the other part is you can sort of think of it as single center solution because they don't have any angular momentum. In fact, it was Ashok who anticipated that this there is a sector, the single center state, that has no angular momentum. So this is polynomial degeneracy, and in fact most of the familiar field theory BPS that we constructed belongs here. Not all, but I have a counterexample to that, but most of them. This side is exponentially numerous, and it is very tempting to at least interpret some of them in terms of single center black hole. However, there are field theory examples like n equal 2 star, where for certain state I have to get a number 1 out of this and number 1 out of this. So it is not all black hole situation. So this is also relevant for some field theory situation. So again, for fun, I have a few more examples. Yeah, I just want to show you the numbers. I mean, it's a triangle case with intersection number 15, 16, 17, and I'm looking only at this horizontal intrinsic invariant part. I have these just large numbers, and a little bit more larger numbers if you have more links. Okay. Now, what this means is, remember when we do real space wall crossing, we transform the problem into many problems where given individual problem represent one partition of the total charge you have. So if you have very complicated quiver or non-abelian quivers, some of those sub-problems will have a basic particle, single particle, what I would call single particle, which is actually one of these looped quiver. Okay, so you can imagine situation where you have, say, triangle like this, but this triangle, if you look closely, actually is itself a triangle. So these are kind of things you should imagine. So in that case, the intrinsic degeneracy that I need as input data actually should know about these horribly large numbers. So this intrinsic part is actually part of your input data, and if you will, it should be a part of your input data for Konsevici-Soiberman. So this need to be put back in. This was achieved. There is a conjecture by, again, Manso, Piljin, Sen. They took this invariant part from us. They wrote equivariant version of that, and they basically told us how to incorporate that into this real space wall crossing formula. Okay, so I think the Jan will start basically tomorrow's lecture with some analog of this formula. So if you can compute this, we essentially have a rather complete routine to compute the BPS, not only discontinuity of the spectrum, but individual the BPS spectrum on the left and right side of the wall. I mean, in practice, this will take a lot of computing powers if your number of particles become large. I think there is a very nice code that the MPS wrote down, mathematical code. I played with it for several months. It didn't go very far beyond 15 particles. So we need some improvement there. And in fact, to me, at least, the most promising way of circumventing this problem that I have to sum over this sub-problem with n factorial number of problem is this notion of quiver mutation. So this quiver mutation has been used in various field theory situations very successfully over the last few years. And I learned about this, I don't know, I mean, I wasn't quite knowledgeable about this quiver representation theory on the mathematics side. This is a couple of references I heard from some colleagues last week. They apparently addressed essentially this quiver mutation from their viewpoint. Quiver mutation is, of course, essentially Seiberg duality that's now applied to quiver quantum mechanics. And you change the rank and number of bifundamentals in this Seiberg duality typically. So you change the rank and you change the intersection number. And along the way, you change basically what you mean by the base particle here in such a way that the total charge doesn't change. So I don't have much time to do this, but there is a fixed set of rules that we all learned from cyborg duality long time ago. That's essentially exactly the same rule. Depending on whether arrow is going out or coming in, one side is affected and the other side is not affected, and so on. So for example, in the simplest two-node quiver, if I do a mutation on that guy, if I'm allowed to do mutation on that guy, I end up with this guy. If I do the other guy, I end up with this other guy. Do it one more time, I get that and that. And one side, you can see that things doesn't really change. It's just, gamma become minus gamma and etc. The right-hand side, things changes a lot. In particular, the rank changes dramatically. And if on top of this, if we know that there is in some set of basis state that you can rely on, some set of hypermultiplet out of which all BPS particle is constructed in such a way the state exists only if this multiplicity of individual particle is non-negative. Okay, and that gives us additional information in such a way that we can completely fix the spectrum, at least hypermultiplet spectrum. So this was done by Alim et al. A couple of years ago, was extended by Shi last year to much more general situation, including SUN. And in fact, this Dan Shi's computation reproduced this the result by Wolfgang Leuchert in year 2000 that computed the spectrum at the Gepner point. So I have a feeling that this Cuba mutation is going to be extremely powerful thing to do, because this in particular changes number of basis particle. So from our real space approach, it may look a little bit strange, but nevertheless, in all example I played with, this seems to be true. So this, because the biggest difficulty in this real space approach, this multi-particle approach, is that the complication due to having many particles. So hopefully this mutation will give us a better tool to deal with that sort of problems. There is a little bit of very intricate chamber dependency or branch dependencies that need to be uncluttered before. So let me summarize. So of course I started with the fact that Kontsevich, Soiberman, and Gayoto Monaitsuke gave us such a big progress beyond what we understood before. There is still some technical difficulties beyond rank 1 and some black hole examples, but of course it's being continuously attacked. On the other hand, there is alternate approach to the problem based on real space picture of the state, a constructive index counting, that has become extremely competitive last few years. And even partial equivalence to Kontsevich-Soiberman has been shown. This comes from quiver picture, where very intuitive Coulomb picture gives us how to count these things, but the much more comprehensive Higgs picture gives us things that we miss in the Coulomb approach, giving us a complete picture, I think. And lastly, this notion of quiver invariant or equivalently wall-crossing safe state seems to be now very important ingredient to this wall-crossing story, especially in the context of black hole degeneracy. And for that, you want to listen to Jan's talk. Thank you very much.
Okay, question?
One.
You had this picture for the cohomology where you had a vertical part and a horizontal part. Is there a simple explanation for why you have only these two parts? And
I mean, this is to some extent artifact of have a single loop and abelian. So in general, what I expect is that this vertical part fattens up. That's because, of course, you can imagine this guy having cohomology like this. Suppose you attach one more particle. Okay, because of this link, everything is Coulomb in a way, because this part can act as if basic ingredient. So vertical part will flatten out. The horizontal part being angular momentum singlet is something you should anticipate, at least in the black hole example, because in the black hole example, this ADS2 times S2 picture sort of preclude the angular momentum quantum number. So if I want to interpret this as a black hole, there is that explanation. More generically, I don't really know.
I realize you undoubtedly explained this already, so I apologize for the question. But what you call the intrinsic part is the idea that it also exists on the Coulomb branch but is harder to see?
Right. Thank you for the question. So when you do the Coulomb branch analysis, in the cases where omega Coulomb equal omega Higgs, the Coulomb branch, the vacuum moduli space, analog of this S2, is nice and compact. In cases like this, if you find the origin is somehow part of that data, out of which, of course, Higgs variable can grow out of. So question is, how do you compactify this non-compact point? Now, the MPS has a prescription how to compactify that, not at the level of index theorem, but in some sense ad hoc prescription. So when I say Coulomb phase result, it's including that prescription. But
I wasn't asking a question about the prescription. If we just talk about the physical theory, forgetting the technique for calculating, is the claim that the intrinsic part, regardless of what's the method to calculate it, does exist on the Coulomb side?
My guess is that it doesn't. It's just the Coulomb description is not good enough.
I don't know what that statement would mean. I'm not talking about a description. Suppose you solve for the exact spectrum of the n equals 2 super Yang-Mills theory in a vacuum which is on the Coulomb branch, and we ask what's the spectrum of VPS particles. The question wasn't meant to be a question about a method of calculating, but about the actual answer.
Oh, you mean this part is really part of spectrum or not?
Well, I'm afraid the question is showing I didn't understand the lecture properly, which I apologize for. But the question I'm trying to ask is, when we go from the Coulomb branch to the Higgs branch, is there a jumping of the spectrum such that this horizontal part suddenly somehow appears? Or is the claim that that part actually also existed on the Coulomb side but was hard to see? Perhaps because the semi-classical methods weren't adequate.
Right. What I'm saying is the Coulomb, what we call Coulomb phase or Coulomb approximation, I think is simply inadequate in such situations. So it's not really good truncation of the full quiver theory.
I don't even know why we're talking about a quiver theory. The problem originally was something like n equals 2 super Yang-Mills of some group and representation, for example. And then when we even talk about a quiver theory, you're getting down to a detailed method of calculation where you might have lost something already. My question was whether the hypothesis is that the horizontal part was present on all branches or only on the Higgs branch.
I mean, they are present in all branches, but only if they manifest in the Higgs description of this quiver theory. I mean,
I don't know.
I think there is a confusion here. Eddie thinking about the Higgs and Coulomb branches of the four-dimensional quantum field theory.
Sorry.
And I think you are talking about something different. Maybe you can clarify.
Oh, is that?
Indeed, of course, I was thinking about the Higgs and Coulomb branches of the quantum field theory.
Oh, I'm sorry. That's the reason I try to stay away from the word phase. So Coulomb and Higgs here is Coulomb and Higgs of the quiver quantum mechanics.
But physically, what justifies comparing the Coulomb and Higgs of the quiver quantum mechanics?
So as I said, this is two different truncation of this quantum mechanics. I think Higgs is much more reliable in the end of the day. Coulomb is good enough for certain situation, but not in all generic situation.
So your hypothesis is that the Higgs answer is the one that should be compared to the underlying field theory?
Exactly.
Okay, thank you.
That's what I say. Yes.
Okay, rest question?
Yes. Maybe I missed it, but there's another physical proof of the Kontsevich-Soibel wall crossing formula using framed BPS states, right?
Oh, that's
Where
right.
you take a line defect or a
That's
very,
right.
very massive black hole, and you study how halos come and go.
Yes.
Okay, so my question is, do you see any relationship between that derivation and the real space wall crossing that you presented?
Yeah, frankly, I haven't really thought about that. I mean, again, there is this halo picture, which is essentially this multi-particle thing.
So let me rephrase the question.
Yeah.
Do you see Fock spaces of halo particles in the real space wall crossing?
Oh,
approach?
yes. So it's, I mean, that picture is some reduction of whatever picture I have in some particular case.
Right, but I mean, the problem with the general multi-centered case was that you couldn't really isolate halos, right? But the idea of the line defects or the very, very massive black hole is that
Right.
you get a core,
Right.
and then you have halos
That's right.
orbiting around the core, and they come and go, and the study of those, of how they come and go, allows you to prove conserved
Right.
Soibel minutes. So I was wondering if there's a way of translating that intuition to
I mean,
your real space approach.
yeah, I mean, in the beginning, we started out treating some of the centers as if it is background, which is similar to what the...
But very, very heavy background, so
Right,
they're in
a
some
very,
sense
very
a
heavy
core.
background. But in the end, what we did is end up treating all particles as dynamical, right? So if I take this picture, take just one, or just moduli such that that guy become extremely heavy, I will just recover what you have. Jeff?
I was wondering when you say black hole, whether you mean an extension of these results to wall crossing for general BPS states in n equals 2 string theory,
Right.
and I guess sort of more generally what the status is of extending this structure to n equals 2 string theory from n equals 2 gauge theory.
Thank you. So that's of course the final aim of this. For example, we saw the exponential degeneracy, so it's natural to compare that against different microstate counting of this. At the current stage, we are starting at the level of any given quiver. So we haven't yet realized how to embed this in a given string theory construction, given Calabi-Yau. That requires another step. So as far as what we did, that's the extension. There might be other work that is trying to, I mean, I guess there are a lot of works actually I failed to mention that doing the other way around. You start with some string setup, rep D4, D2, D0s, and count individual case. But that wouldn't be a generic counting like this. So, I mean, and both sides need to approach each other, I think. So we are not quite there yet.
Okay. Okay, only the last question.
So from the Hodge diamond, this look like a Calabi-Yau manifold. Is that coincidence or?
Oh, this is just coincidence. It doesn't have to be. Of course, this is mechanics, not two-dimensional GLSM. So yeah, I'm sorry. There are of course Calabi-Yau cases. That simply happens because the example here is that the number of charges coming in, number of charges going out is always equal. So that's Calabi-Yau situation. Generically, no.
Okay, so let's thank speaker again for his very nice talk.
Much.